first presentation today is by Dr. John Nielsen Gammon. He is a Regents Professor at Texas A&M University, Director of the Southern Regional Climate Center, and the Texas State Climatologist. Dr. Nielsen Gammon grew up in Northern California, went to school in Massachusetts, receiving a PhD from MIT in 1990. Dr. Nielsen Gammon joined the faculty of Texas A&M in 1991 and was appointed Texas State Climatologist by then Governor George W. Bush in 2000. He just completed a 2-year term as president of the American Association of State Climatologists. He was named a fellow of the American Meteorological Society in 2011 and a fellow of the American Association for Advancement of Science in 2024. Dr. Nielsen Gammon conducts research on large-scale and local-scale weather, climate, and air pollution with a focus on intense rainfall and droughts. He teaches courses in weather analysis and forecasting, climate and climate change, and computer modeling. Please welcome Dr. Nielsen Gammon.
All right, try that again. Thank you very much. I probably win the prize for traveling the longest distance here since I'm from East Texas or Southeast Texas, and I've been being in College Station. And so having me talk about the local climate is a little bit weird because the way you find out about the local climate is you ask people who've been here a long time. The best I can do is look through a narrow window at West Texas and tell you what I see through the data that I have access to. So I'll be translating the data into meaningful information, and hopefully those of you who know how to do that better can speak up and offer your own anecdotes and stories either during or after my talk or during the rest of the day. So when we're talking about weather and climate, there's lots of different factors to consider. The things that drive the weather tend to be, at least most important, the rainfall amounts, which defines West Texas as being an arid or semi-arid environment, depending on where you are. Temperature doesn't make a desert, but it certainly affects the landscape considerably. And of course, the energy for everything coming from sunlight, which in West Texas there's plenty of. When you think about climate, you're typically thinking about perhaps what the normal conditions are in a given location. But in reality, the things that matter for the climate and for what happens on the land are the extreme conditions. How hot can it get? How cold can it get? How long do you have to go without rainfall? That sort of thing. And so I'll be talking about average conditions and also the extremes. And in West Texas, we have most of those extremes to deal with. We've got drought and aridity here as two separate bullet items because the distinction is aridity is when it's normally dry, and drought is when it's abnormally dry. So in West Texas, you start off generally with arid conditions, but then you have drought on top of that can make things really difficult. And the consequences for drought in West Texas are different from many other parts of the country that start out with a lot more water available. And then we also have heat and cold. Heat advisory today, I believe, but it also gets quite cold in the wintertime, and so we experience large swings in normal conditions as well as the extremes. Now, every place on Earth's weather is governed by where they are on the planet. In broad scope, you all know it's warm in the tropics and cold at high latitudes. But the wrinkles that come on that are literally the wrinkles on the Earth's surface. We've got oceans, we've got continents, we've got mountains, we've got valleys, and those all shape the landscape. The three primary factors affecting conditions in West Texas, where we are right in here, are, first off, the mountains. The mountains matter locally As a general rule, the higher up you go, the cooler the temperatures, at least during daytime, and the greater the amounts of precipitation. But in a broader sense, we've got mountains going all the way up from Mexico to Canada and Alaska. Generally speaking, that's called the North American Cordillera. And in particular, we've got mountains in much of western Mexico that are higher than the mountains in West Texas. And these mountains in general form a barrier to air that would like to travel from west to east, particularly during the winter time. Except there's a couple of gaps in the mountains. There's a bit lower in Washington, Idaho, and Montana, and they're considerably lower along the southern border, southern Arizona, New Mexico, northern Mexico, and West Texas. And so on a large scale, those gaps are where air is able to travel from west to east, and we tend to have fairly strong winds when that does happen. We also get moisture from the Pacific Ocean, particularly in the fall and winter, but that moisture is depleted by virtue of the fact that it has to travel over those mountains. The other source of moisture is the Gulf of Mexico, and that works mainly during the summertime to provide moisture, although we can get moisture from the winter from there as well. This geography also affects our temperatures in West Texas. The distance from any oceans means that West Texas has a continental climate. Temperatures can swing widely from day to day and even from daytime to nighttime. And being this far from a moisture source means that humidity levels tend to be low. Also, being close to the western edge of the Atlantic Ocean means that in the summertime, winds tend to be moving from south to north. In the winter, oftentimes they're moving from north to south. And these mountains to our north form a sort of a barrier to air that would like to spread out horizontally, but instead it can't, and it's channeled southward along the Rocky Mountains, and then finally finds lower topography in West Texas and channels through the gaps in the mountains. So the cold air in West Texas comes from the north and most immediately from the northeast as the air is sneaking its way through the gaps in the mountain ridges. So there's no other place on earth that has that combination of factors. So weather in West Texas truly is unique in that sense. Next, I'm going to walk you through some maps of normal rainfall on a month-to-month basis and emphasize how unique things are. We can take a look at average precipitation in West Texas. It ranges from less than 8 inches in some of the lower terrain to the north to as much as 20 inches in some of the higher peaks. If you look around at that map, you can find a few areas with similar sorts of colors. I'll highlight a couple to draw the contrast. West Texas annual rainfall looks a lot like annual rainfall in, let's say, north central Montana. It looks a lot like annual rainfall in, let's say, Southern California, although there's bigger variations in Southern California. But certainly the dryness in West Texas is part of the western United States being relatively dry. Now, on a month-to-month basis, we can start with January. And yeah, West Texas still looks a lot like Montana, but completely different in Southern California. In arid places along the West Coast, you tend to have a wet season and a dry season, but the wet season is in the wintertime and the dry season in the summer. But as you move into the area downwind of the Rocky Mountains, the dry season is in the wintertime, the wet season's in the summertime. And the main reason for that is during the wintertime, the winds do prefer to move from west to east. And so that same mountain barrier that's preventing moisture from making it into West Texas is producing rainfall on the upwind side along the Coast Range and Sierra Nevada and so forth. Let's step forward a couple months to March, and you may notice at this point, West Texas and southern New Mexico is the driest area on the entire map. It's dry in the spring for several reasons and several contributing factors, including the lack of rainfall. Also, as you'll see, the winds from the west tend to be strongest at this time of year, so there's downslope flow that dries things out some more. We don't get moisture from the Gulf of Mexico yet, and it's even drier than most of the Mojave Desert because they're still getting some moisture coming in from the Pacific Ocean. Step forward a bit more. April, getting a little bit wetter. Wetness is sort of progressing on these maps from east to west, which is sort of analogous to the moisture making it farther and farther inland from the Gulf of Mexico. And as we hit July, we now have, and August, we've got now the wettest time of the year. It's even wetter now in West Texas than it is in Montana, and definitely wetter than in California, where, in fact, the Davis Mountains are getting almost as much precipitation as the Olympic Mountains in Washington. In September, in particular, August and September can get moisture from decaying tropical systems, and that makes August and September in particular the time of year when the region is most susceptible to flash flooding. If we step forward through October, November, December, things are drying out again, and we've made it through the entire yearly cycle. Temperatures are to a large extent determined by latitude, as you might expect. You get more sunlight the farther south you get, closer to the equator, the sun's more directly overhead. And so these stripes of temperature bands are going from east to west, and West Texas really fits in fairly nicely with the rest of the United States at that latitude, with high temperatures during the daytime, somewhere averaging around the 50s, even averaging the 60s down around the Big Bend region. The daytime lows in January are now colder in West Texas than they are at similar latitudes. And that's because West Texas is farther from the oceans. There's less moisture. And so as a general rule, there's bigger swings of temperature from day to night, in addition to having fairly large swings in temperature from one day to the next because of traveling weather patterns. In the summertime, West Texas is, at least many parts of West Texas are the coolest parts of Texas itself, mainly, almost entirely due to the higher elevations. If you had if you were to launch a weather balloon in the middle of the day on July, you'd find the temperatures decreasing by about 25 degrees Fahrenheit for every mile of elevation you gain. It doesn't quite work that way if you're driving up a mountain, because the sunlight is heating up the ground on the mountainside, and that's heating up the air. That means that in a mountainous region like this during the summertime, the air near the mountains is hotter at that elevation than the air over the plains and over the valleys. And that temperature difference drives daytime wind circulations, which in turn can trigger thunderstorm activity, which is going to form primarily over the mountains initially. At night, so the opposite thing happens. The ground is cooling, it's radiating energy out to space, and so the air close to the ground gets cold, whereas out over the valleys, the air is about the same temperature it was during the daytime. And so now the winds between the mountains and the valleys reverse, and you get air flowing down the mountains, much like water would if it was raining. Just following the path of least resistance down the mountains and flowing into the valleys, and pools of cold air forming in the valleys and getting deeper and deeper during the nighttime. As a consequence of all of that, the mildest temperatures actually tend to be somewhere on the mountain slopes, between the mountain peaks and the valleys, where air doesn't get as cold at night and it's warmer during the day. And you get very large variations in vegetation along mountain slopes as a result of all of those things going on, and it matters whether you're within a canyon along the mountains or sort of on a height of land in between those, because the wind drainages are different. Okay, I've showed you some maps of rainfall. Now I'm going to show you some graphs of rainfall. And this particular example is from Mount Locke. There's a long-time observatory at the top of Mount Locke, which has been taking good climate data for a long time, so gives a good example of the weather in the mountains. And we're looking at what's called accumulated precipitation. How much rain, well, the current time, at least when I made this map, which was about 4 or 5 days ago, is right here, and we can go back a month, 2 months, 3 months, 4 months, 5 months, 6 months. And the thick black line is how much rain has occurred since each of these times. So Mount Locke has gotten, let's see, here's 5 inches. It's gotten about 1.5 inches, mainly in early July. It got another 1 or 1.5 inches in late June. Before that, 0 precipitation for 3 months solid. And there was a little bit of rain in March, a bit more in the very beginning of March. So far, since the beginning of February, Mount Locke has gotten about 3.5 inches of precipitation. Now, all the other colors on this graph are historical values of rainfall at the same location. The dark red corresponds to the driest 2% of all years in history. On the graph here, we've labeled that D4. That's based on the United States Drought Monitor's classification of drought. They've got 5 levels from D0 to D4. D0 is abnormally dry. That's conditions that happen maybe 20 to 30% of the time. Then D1 is moderate drought. Happens 10 to 20% of the time. D2, extreme severe drought, which is 10 to 5%. D3, extreme drought, 5% to 2%. And then exceptional drought is the bottom 2%. And some of the drought relief programs from the USDA are based upon these sorts of drought levels. If you're in D2 for a long enough period of time, or in D3 briefly within a county, you're eligible perhaps for drought relief. Now that's based on the drought monitor itself, which takes into account lots of different indicators of drought. This is just one indicator, which is rainfall. It's the most important one. We've also got things like temperature and wind and so forth that are affecting how dry the landscape gets. So we've got those colors. I've got blue colors on the wetter side with labels that sort of are the mirror image of the dry conditions. So 70th to 80th percentile of rainfall, 80th to 90th, and finally the dark blue is the wettest 2%. And then the thin white lines are the extremes. So how much rain has ever happened over the past 1 to 6 months, ending at the end of July. And we see some pretty big extremes here. There has been a year with only about 1 inch of rainfall over the past 6 months, from February to July at Mount Lock. Conversely, there's been a year with 20 inches of rainfall during the same period. That's a factor of 20 range. So one thing to keep an eye on as we look at different locations is how big that range is, how wide the range of possible conditions are. Lastly, this black line in the middle of the white is the median. That's half the years are wetter than that, half the years have been drier than that. And this shows basically that typical conditions aren't a very good guide to what the actual conditions will be, because year to year can vary quite a bit. 2010 was quite a bit different from 2011. On this plot also, you see a fairly angled line going to the middle of May, and then a fairly flat line since then. That shows how abrupt the transition is between the dry season and the wet season. We start getting precipitation in the mountains in mid-May, and it persists through July and August and September. On the right is the same sort of plot, but over a longer period of time, covering 5 years. And it looks like a set of stairs. The rainfall is fairly flat during the wintertime. There's very little that accumulates, and then you get most of the rain in the year happening during the summer months. So you can pick out the summers on this plot. And in this particular year, this current year, Mount Lock has been unusually dry. If you look at precipitation since the middle of May, which is a good marker for the wet season, it's been around D2 or D3, so about as dry as, say, 5 years out of the century, which is pretty dry. Looking at the longer period of time, we find we're sort of in the same range. So the past 5 years have been around the 5th or 10th percentile, so only 5 or 10 years out of the past 100 have been this dry on a 5-year time scale. Let's see, the only other thing I haven't talked about on this, the one-day record, how much rain you can get in a single day. And you can get as much in a single day as you would normally get during a month and a half during the wet season. Now, for a drier location, I've chosen Panther Junction down in Big Bend National Park. It's near mountains, but it's on the desert floor, and average rainfall is quite a bit less. The median in 6 months is about 5 inches. compared to Mount Locke being 7 or 8 inches. And the range of conditions is also fairly broad. Colors spanning the whole right-hand edge of this graph, and you get the same stair-step pattern, although over the long haul, it's been fairly dry there. If we look at the past 4 to 5 years, it's a record dry 4 to 5 year period at this particular station. And another station even farther south, Castellon, which is on the Rio Grande, and looking similar. It's historically dry over the past 5 years there. Conditions have literally, over the past history, ranged from almost 0 rainfall to over 10 inches of rain. So the challenge is dealing with the feast or famine that can occur. Also, it's feast or famine on a daily basis. They've gotten about 3 inches of rainfall this year, most of which have happened in 2 days, one in early July, one in early June. So it's not like you can get steady rain. It's either you're going to get hit by a thunderstorm or you're not going to get hit by a thunderstorm. Now, for perspective for other locations, here's Dallas, for example. You see the range of possible conditions over a 6-month period is not as broad. Well, we're going from, say, 8 inches to 35 inches. So that's a factor of 4, maybe a factor of 5 variability compared to the factor of 10 or more that's possible in West Texas. Also, July in Dallas is the driest month, climatologically speaking. They actually have 2 wet seasons, mainly in spring and fall. And in the summertime, they're getting as much or maybe even less rainfall typically than West Texas is getting. For that reason, you don't see the stair-step pattern in the typical conditions. And also, in Dallas, it's been fairly wet the past few years. Same sort of thing for San Antonio. They've been really wet this month, gotten almost 5 inches, although they've been dealing with a long-term drought where the past 3 years or so has been among the driest in the century. Other parts of the United States look even more normal. Here's New York City, where the range of possible conditions only varies by a factor of 2 or 3, and it's very steady throughout the year. San Francisco, we get a stair-step pattern, but as I mentioned, in the West Coast, it's the opposite. It's wet in the wintertime, and it's very dry in the summertime. This is a plot of, I've chosen Fort Davis to show daily temperatures. And the temperature, the scale is on the left, 100 degrees Fahrenheit is here, 0 degrees is here. The top line is the record. So Fort Davis can reach 100 degrees anytime from mid-May to early September. The bottom is the record cold. So it has gotten down to 0, but not below in Fort Davis. The orange shading is normal, maximum and minimum temperatures for the day, and then the blue is what's actually happened this year for the past 7 months or so. And what I want to highlight here is 2 things. First off, how much more variable the weather is in the wintertime than the summertime. You've got a much bigger range of possibilities in the winter than you do in the summer. And then also, the gap between normal, maximum, minimum temperatures is fairly large in the spring, and then it narrows during the summertime. As we get more and more moisture coming in the summer and get more rain, that tends to elevate the humidity levels, and it makes the nighttime temperatures not as cold compared to daytime as they were earlier in the year. So air doesn't cool off as much. The last set of data I want to show you are something called a windrows, which are really cool if you know what you're looking at. In this case, imagine you're looking at the compass with north being up on the top, south on the bottom. Here's east, here's west. And so we're dividing the compass into 36 10-degree segments. And in each segment, we're plotting the percentage of wind events from that direction. And the colors indicate how strong the winds are with the scale on the bottom. So orange is 15 miles per hour or greater, for example, and dark red is 20 miles per hour. And this is for Marfa Airport. And we see the winds predominantly during the daytime. This is from 9 a.m. to 8 p.m., predominantly from 3 different directions, from the west, from the south, and from the northeast. Why those 3 directions? Well, it comes down to topography. We're located here, and there's mountains to the northwest, so we're not going to tend to get air moving from there, but air can pass along the valley from the west. It can come out from the south and southeast, and if it's going to come in from farther east and north, it's going to come in through from the direction of Alpine. So those 3 wind directions are a reflection of how easily the air can move from different directions. That's daytime. Here's nighttime, which looks completely different. Winds predominantly from the north at night, and that's because Marfa is located on a sloping terrain with higher elevation to the north, lower elevation to the south, and so those nighttime drainage winds I talked about are predominant at night, and it doesn't really matter much what the large-scale weather pattern is. The wind most of the time is going to be from the north. If we look at things different times of year, here's January. So the warm air is typically coming from the west, the cold air is coming from the north or northeast. April, same basic pattern, although if you compare to January, you see a lot more oranges and reds. Springtime is the windy time of the year, and that's the other reason that the springtime is the driest in West Texas. Not only is rainfall at a minimum, but the wind speeds are largest, and the stronger the wind, the stronger the evaporation rates if you had water to evaporate. In the summertime, the wind is predominantly from the southeast and east. That switch in direction has the technical name of a monsoon. When you have winds in the wintertime predominantly from one set of directions, and winds from the summertime predominantly from a different set of directions. Now, in popular imagination, we associate the monsoon for weather in India and rainfall. That's because wind direction really matters for rainfall, as it does here in West Texas, because the southeast winds are allowing Gulf of Mexico moisture to penetrate into West Texas and produce rainfall. So the rainy season during the summertime is part of the southwest monsoon. And then in October, start getting the cold fronts again from the northeast. Let's look at another location, Alpine. So we're out here now. We're on the other side of this range of mountains, so it's not going to be as easy. It's not going to be as easy for the wind to come from the south. But air coming through this gap of the mountains is going to then basically be going through the gap there. And you're basically stuck with southwest winds most of the time during January. And even in April and July, you get some southeast winds, but also southwest winds tend to persist. And those southwest winds are mainly nighttime winds. The southeast winds are the daytime winds with the air moisture coming in from the Gulf of Mexico. And they're back to October, you lose the moisture again, you've got winds from the southwest. But compared to April, when you had strong winds from the southwest fairly frequently. In October, the wind speeds are a bit weaker. And the last place I want to look at is Presidio down here. Now, you might think the wind would be coming down this valley, but this valley is ringed by mountains, and so there's not a lot of air that can come through there. Similarly, you've got the canyon through here where air can't really pass. So it turns out there most of the wind is from the north. And in the summertime, it's from the northeast, which topographically means air is coming from the Gulf of Mexico, then making its way through the area north of Big Bend, and then coming into the Presidio Ojinaga area. Okay, so in the title, I was supposed to talk about all of these. I've mentioned monsoon rain. I mentioned drought. I've talked about flooding a bit. I've talked about wind. I guess the only thing I haven't mentioned explicitly is fire. So the time of year when you can get fires is mainly in the springtime and summertime. Summertime, you've got potential for ignitions from lightning, particularly during the early summer season because things haven't greened up yet. But in the spring, where all the grass from the previous summer has gone dormant or dead, you've got the strong winds, and that's when wildfire can spread rapidly, and it's perhaps the most dangerous time of year for fire. But having the dry period and the wet period means that you've got a period of time during the year when things are dry and fires can absolutely take place. I haven't talked about climate change because the climate as it is challenging enough. Things you can expect in the future, a bit of an upward trend in temperature, rainfall a bit more variable than it already is, soil's a bit drier and vegetation a bit lusher, which sounds contradictory, but actually carbon dioxide is causing both of those things to happen for different reasons. I'll be happy to answer questions here, and if you need to follow up with me later, there's my email address. Thanks for your attention.
I've always heard in the Trans-Pecos that you always wanted to get the first rain because moisture drew moisture and it would kind of come back there. Do you think there's anything to that?
I personally don't think so. I think that what's happening is with the first rain, you're getting the weather pattern changing, and once you start getting the monsoon, it's going to persist. So there's an indication that the rainy season started early and it's going to last longer. But the rain itself isn't facilitating more rain except to the extent that as the water evaporates, that can help add to the moisture in the air and can contribute as well. But it's mainly the moisture coming from the Gulf of Mexico that's the source.
Have you, thank you for coming all the way here to Marfa, by the way. Have you seen any or heard anything about, say, the depletion of grasslands like the Great Plains, prairie, changing what's on the ground, affecting climate, or even water, rivers, et cetera?
Yeah, so this is basically the same as the previous question, but on a longer time scale. As you get the more vegetation you have, the plants are transpiring and adding water to the air, which can then feed into more precipitation as well. And because they're drawing that moisture from the root system, it's not just the topsoil that can dry out. So you end up with more rapid cycling of water within the landscape as a result of that vegetation. Also, vegetation tends to be darker than dry vegetation in soil, so that gets more solar radiation coming in, although then the moisture produces more clouds, which can be a moderating influence. It's all a lot of different factors at work, but for example, in say the southern high plains, there have been studies that showed that all of the irrigation that's going on, pumping groundwater from the Ogallala Aquifer and laying it on the landscape, has led to an increase of precipitation downwind in, say, western Kansas and Nebraska. That's happening on a much larger scale than conditions here, although we'll hear a bit more about vegetation changes later on today, and that is both in response to climate changes, potentially, and also driving climate changes.
Any other questions? It's our chance to have a world-renowned expert in the room on climate. So some of those, I think everybody out here thinks about climate a lot.
Yes, sir. Okay.
How big of a factor is what goes on in the Pacific with the El Nino and La Nina in our weather?
Yeah, El Nino and La Nina affect the weather in West Texas mainly by altering the location of the jet stream. El Nino, when the tropical Pacific is unusually warm, that tends to bring the jet stream a bit farther south, and so there tends to be more precipitation in the wintertime than normal in West Texas. La Nina, the opposite. It's cooler in the tropics, and the jet stream tends to be farther north. So you tend to have drier conditions in the wintertime. Of course, it's normally dry in the wintertime, but that tends to add to it. It also affects temperatures a bit. We tend to have milder winters with a La Nina than we do with an El Nino. And right now, we're in neutral conditions in the Pacific, 80% chance of La Nina by this winter, so we're looking at drier and milder conditions than normal this wintertime. And things fall into place like that about 2 years out of 3, so you can't hang your hat on it, but it's a definite tendency.
So following a spike treatment of 2 to 5,000 acres, and you have that large change in vegetative characteristics, less brush and shade, and I guess what you're talking about, color, that changing, what impact does that have on a local precipitation? Like when I see rainfall in this pasture 5 miles this way and then nothing dropped over here, is there anything to consider, on that 5 to 10 year scale?
I don't think there's much that the local land conditions on that scale can do to affect precipitation compared to, say, the nearby mountains, which are huge, literally and figuratively. One thing that tends to enhance precipitation in the summertime and allow convection to develop earlier is when you have large variations of conditions on the ground, but it has to be on scales of tens of miles for you actually to be starting affecting the winds and then affect the updraft currents and trigger those wind circulations. Something small scale, you might be able to feel it locally, but you have to be affecting a mile thick layer of air to make much difference.
The topic of cloud seeding came up in conversation yesterday on a ranch visit, and I wonder what your thoughts are on that. I don't know if they're still doing it around Fort Stockton, but how successful are those programs?
It's hard to say. It's easy to see that there's a bit of an enhancement in the wintertime with mountain-produced precipitation. It can enhance precipitation by about 5 or 10% under those conditions. In the summer with thunderstorms, things are quite a bit more random. Optimistically, maybe a 5% enhancement. The challenge is it doesn't fill in the gaps very well. It's 5% on top of what would have happened that year anyway. So droughts are still going to be droughts, no matter what.
Last summer was supposed to be El Nino. We expected maybe higher rainfall, but I saw some discussion. There was people wondering how would the El Nino relate with the Hadley cells and the dry air coming down. And last year it seemed like the Hadley cells won and the compression won out. Any comments on that?
You talking about during the summertime? Yeah. There's not any reliable relationship between El Nino and rainfall in West Texas in summertime. About the only effect it has on summertime conditions in Texas is changes in the frequency of tropical systems. It's pretty rare for that really to have much effect here. You can get some rain from an Atlantic system, potentially, if it follows the right track. You can get rains from the remnants of a East Pacific system, but it's sort of one or the other. La Nina is going to tend to make Atlantic cyclones more likely and East Pacific cyclones less likely, and El Nino vice versa, so it really doesn't make much difference overall.
Are there any cloud seeding projects in this area that you can speak about?
I don't know. Probably somebody else in the room might. I know there's a lot of cloud seeding activity in the western half of the state in general. Okay, thank you again.
Thanks so much.